When a massive grid fault occurs, a synchronous generator experiences intense electrical and mechanical turbulence. Predicting whether the machine remains synchronized requires complex dynamic mathematical models. We're tracking hundreds of tons of solid steel spinning at thousands of RPM, reacting to sudden voltage spikes and physical vibrations. To capture this behavior, engineers rely on the D-axis and Q-axis equivalent circuits. This framework maps all the electrical pathways inside the machine, including the stator, the field winding, and the damper windings. This creates a dense web of parallel branches. Every inductor and resistor in this model reacts to high-speed fluctuations in current and magnetic flux. Solving the differential equations for these multi-axis circuits requires significant computational power. That level of detail is necessary for sub-second faults, but unnecessary for monitoring standard operations. For steady-state operations, engineers must mathematically collapse this dynamic web into a static representation without losing the core data that defines the generator's power output. We start with the assumption of equilibrium. The generator's rotor speed is constant and locked to the grid frequency. At a constant speed, the system is not oscillating. Mathematically, the differential time operators, represented by the variable p, for all flex and current equations equals 0. By forcing these time derivatives to 0, we can strip away the transient branches and derive a single phasor equivalent circuit. This linear mathematical circuit is the first step. To accurately predict power flow, we must then apply empirical data to correct for the physical magnetic limits of the machine's iron core. To execute the mathematical collapse, we look directly at the time derivative operators, p, within the D and Q circuit equations. Because the generator is at steady-state equilibrium, every one of these derivatives is set to 0. This has a direct physical consequence. Damper windings only generate current when they cut through an oscillating magnetic field. When the oscillation is removed, no currents are induced. The damper winding currents drop to 0, allowing us to remove their influence from the model entirely. Next is the field winding. During a transient, this branch carries dynamic flux, but at constant speed, the flux is static relative to the rotor. Its derivative also drops to 0, and the entire branch becomes a simple short-circuit equivalence. Steady-state equilibrium effectively neutralizes the generator's internal transient pathways, leaving only the core stator parameters to manage. For modern round rotor generators, the physical structure of the remaining D and Q axes exhibits near-perfect magnetic symmetry. This symmetry allows engineers to consolidate the two separate axes. Redefine a single internal voltage source, EQ, which is proportional to the field current. Simultaneously, the reactances from both axes combine into one unified parameter, the synchronous reactance, XQ. This yields a single algebraic equation. Terminal voltage equals the internal voltage minus the voltage drops across the stator resistance and the synchronous reactance. The equations now match the standard schematic used for steady-state analysis. While the algebra is precise, we can better visualize the machine's operation by translating this equation into a geometric phasor diagram. Grid operators control power flow by adjusting the internal rotor angle, delta I. However, this internal variable cannot be measured directly by sensors at the generator terminals. To determine it, we translate our steady-state equation onto a Cartesian scene, starting with the measurable terminal voltage, ET. We establish ET as our baseline reference vector at 0 degrees. Under standard load, the measured terminal current operates at a lagging power factor relative to this voltage. We plot this lagging current vector, IT, at the angle phi. Now we track the voltage drops inside the machine. First is the drop across the stator resistance. Because resistance is a real value, this voltage drop runs parallel to the current. We append the resistance vector to the tip of the terminal voltage vector. Next is the synchronous reactance drop. In our equation, this reactance carries the complex operator J, which dictates a 90-degree counterclockwise rotation. From the tip of the resistance drop, we draw the reactance drop at a perpendicular angle. We have traced the voltage from the terminals, through the resistance, and through the reactance. Connecting the origin to this final point completes the polygon. This resultant vector shows the magnitude of the internal voltage, EQ, and its angle. Extracting this internal angle, delta I, through geometric deduction provides the exact mathematical parameter required to calculate a generator's active power limits. This linear model assumes that as you increase field current, the magnetic flux linkage will scale up proportionally and infinitely. In reality, the iron core has a finite capacity to carry magnetic fields. Once the physical material reaches a certain magnetic density, it can no longer absorb more flux, it saturates. Beyond this point, it requires significantly more field current to produce even a marginal increase in magnetic flux. Manufacturers use an open-circuit characteristic test to empirically measure this threshold. If the generator never saturated, the test results would plot as a continuous straight line. This linear path is known as the air gap line. The actual test data shows a divergence. As field current increases, the curve flattens. The real machine's performance deviates from the ideal line as the iron core reaches its limits. Using only the linear assumption in simulation software results in an overestimation of the generator's reactive power capability and its stability margin. To correct the model, engineers must quantify the gap between the theoretical air gap line and the physical saturated results. Standard industry practice assumes leakage flux is unaffected by saturation, so the correction factor is applied to the D-axis mutual inductance. The saturation factor, K sub D, is the ratio of actual saturated flux to theoretical unsaturated flux at a given field current. Commercial tools use this ratio to adjust the machine's reactance based on its operating point. Tools like PSSE or TSAT require these curves to be converted into a segmented mathematical function. The curve is divided into a three-segmented architecture: a linear segment, an exponential deviation curve, and a final heavily saturated linear slope. This segmented approach allows the software to calculate the correction factor for any level of field excitation. By collapsing transient dynamics into a steady-state phasor model and applying an empirical saturation factor, engineers create a simulation environment that matches the actual magnetic and thermal limits of the generator.